Now we know already a little bit about the design of the Internet protocol. We know the characteristics and what the IP, the protocol, can do. We also know, well, there are many things missing. So there are still many open questions, and this is exactly the topic of this subsection. So we need some additional helpers that this ecosystem IP really works on the network layer. So what are the open questions? Well, okay, we have an IP address on layer 3, but how do we get the layer 2 address? We all know already that we need the MAC address, layer 2 address, for example, an Ethernet frame. So we need a source address and destination address. How do we get it? We learn ARP, the address resolution protocol, can help here. How, maybe, if you want to map a link layer address, so MAC address, to the IP address. So how can we do this? Why should we need this? There's also a little helper. I will come back to this, why we maybe don't need this any longer. So what happens if something goes wrong? IP itself, that's best effort. IP doesn't care. So this is why we have ICMP, the Internet Control Message Protocol, that can send back certain error messages. Then how do we get IP addresses at all? So if we don't know an IP address, we learn a little bit more about DHCP, NDP, etc. Then how to establish paths to the internet, routing, all these things. That's a little bit more complicated. And then also, how can we efficiently communicate with several end systems? I will talk then about multicasting. So first of all, how do we deliver packets in local networks? Okay, so let's assume this is our very simple local area network, and we all know that we need certain addresses. We need addresses, ports as we call them on a transport layer. We need the IP addresses. We need MAC addresses, so the address on layer 2. So if we have the IP address, how do we get the corresponding MAC address? Because yeah, it's nice if you know, okay, the IP address of this computer, IP address is whatever, 129.13, let's stay with IP version 4, faster to write, something like this, and the IP address here is also something, you know, and now you want to send a packet over to this computer. Nice, you know the IP address, but we all know we have to go down the stack. So we need the MAC address, because if we want to form a packet, we need here the layer 2 address. Okay, how do we get it? The corresponding MAC address. Okay, so this is where we can use the Address Resolution Protocol, ARP. So this protocol discovers the MAC address that is associated to an IP address. So the hardware cannot handle IP addresses. So hardware works with layer 2 addresses. In the local area networks, we learned that we can use the MAC addresses for forwarding the packets. We learned about spanning tree protocol and all these things. Okay, so now ARP, this protocol helps us to map the IP address to the hardware address. So that's the idea. How can we do it? We will see in a little example. We use a local broadcast. So if we do not know who is responsible for this packet, I only have the IP address, all I can do is I send a broadcast in my network, and then hopefully someone will answer. This, by the way, is also a reason why we cannot have worldwide layer 2 networks. So worldwide broadcast, that's a problem. So how does it work? So now let's assume we have the following situation. We have the computers, as shown in the simple examples, with IP addresses. So this is my layer 3 address, but also all the interfaces have layer 2 addresses. And I want to send a certain packet to a computer. For example, from this one over to this computer. All I know is the IP address. How, etc. I will come back to this later. Then all I can do is I send a so-called ARP request. Who has the IP address 160.45.013? But I already need a layer 2 address, but I don't know the layer 2 address of the appropriate computer. So this is why I use a broadcast. A broadcast, that means that this packet, the ARP request, will go to all stations connected to the local area network. So switches will forward broadcast packets to all ports. So then all the stations will receive it, broadcast. Okay? And then, hopefully, there's also the computer with the right IP address. Yes, it's this one. And the idea then is that this computer will answer. Okay, sending back the response. I'm the one. And I tell you, this is my MAC address. And this is now how the computer learns the MAC address that belongs to an IP address. And the hosts now store the IP and MAC address pairs in a table, the so-called ARP cache. And typically those entries, they become invalid after a certain time because maybe computers migrate or you assign a different IP address or whatever. So that's the idea. There are different ways of optimizing this. So for example, computers occasionally send ARP address to its own IP address just for refreshing the entries. So that's the idea. Or in some systems, the host periodically sends requests for all addresses listed in the cache just to update the cache. That's the idea. So you refresh the entries. Okay, so how do we then deliver packets in our local network? Okay, that's what we learned. But end-to-end, that's a bit different. Now, assume you're located in one local area network here, and you want to send a packet to a computer in another local area network, maybe in a different city, different continent. So maybe there's the internet in between. Here, we show only one router. So now, which destination MAC address should I use here? So MAC address, so what is the layer 2 address, destination layer 2 address? The point is, if I don't know anything, we just learned, we will send an ARP request. ARP request, who has, I want to send something to 141.45.20.20. Who has this address? This packet will go to all machines connected to the local area network. One computer will say, okay, I'm not the one. But then we have a router. The router, as we learned, has an IP address that matches to the local area network here, to the subnet. And now it's a special situation. In this case, for all packets with destination outside the local area network, like in this example, the router will answer. So if you send an ARP request, what is the layer 2 address of this IP address? The router will answer, although the router doesn't have the IP address, but the router is responsible for forwarding the packets to this other external machine in a completely different local area network, maybe in a different continent. So now there's the ARP request, the router will answer with a response and telling the machine, okay, for this IP address, I'm responsible, and the router will tell its hardware address, so the MAC address of this interface here, that's the content of the ARP reply. So then the computer knows, okay, I can now prepare a layer 2 packet using the destination MAC address of the router. So why is this the case? Because, as we learned, layer 2 is valid only from one MAC interface to another one. That's one layer 2 association. So, between one computer and the other one. But only within local area network. A layer 2 connection never goes across a router, so it ends there. And then in this very simple example, the router will then create a new layer 2 packet, again a layer 2 packet, with now the destination MAC address of this destination computer, and the source MAC address is now the MAC address of the router interface here. The router will not change the layer 3 packet, but it will change the headers of the layer 2 packet? Well, actually, it decapsulates the layer 3 packet, takes it out of the envelope, layer 2 packet, and then creates a new envelope, a new layer 2 MAC header. So that's the idea. Okay, so if someone asks you, what is the MAC address if you send a packet to some distant computer in Tokyo and you live in the US, then always think, what is the first router? That's the MAC address we use, not the MAC address of whatever computer in Tokyo. We don't know this one. We cannot find it out, and no one will tell us. Okay, so that's the idea of delivering packets end to end. We haven't solved the question of how do we find all these hosts on layer 3, and how do we find where to send to, how do we find all this. Haven't discussed this. This is something about forwarding and routing. Here it's all about, first of all, layer 2 MAC addresses. So ARP works in a local area network. So that's the basic idea. ARP has a special packet format specified. You see, it's quite old protocol, 1982. And it can be used in many network layers, link layers, etc. But typically we operate on Ethernet, Wi-Fi, and have the IP protocol. That's the idea. So this is how those packets look like. So with where you place all the addresses. So nice, 1982, the world was still nice because only some universities had connections to this kind of internet, ARPANET, all these predecessors. But ARP has also many problems. Because ARP, you can do ARP spoofing and you can do something that's called cache poisoning. Well, what does it mean? If you look at the standard, so ARP is a request response scheme, stateless. And no one authenticates anything. So machines trust each other because the basic idea was, well, this is a local area network. Well, it's under your administration, you take care. So what's the problem? And only you can afford machines, computers are expensive, etc. 1982. So, okay, so you trust each other, and if you send out an ARP request and you get a response, you trust the response. So you update the cache each time you receive an ARP reply. You do not check if this makes sense or whatever, even if you did not send the request. So if you just receive a reply, you read out, okay, that's the MAC address that belongs to this IP address, and you update. And now if you have some really rogue machine, you can spoof the machines by replying with wrong data. That's one of the tricks. So you just, if there's a request or not, that doesn't matter. You just reply with wrong data. And the idea is then you can poison the cache and you just send replies. So how does it work? Very simple. Well, you have your nice machines, the lower ones, and you have your evil machine, the upper one. And this is just maybe some laptop connected or whatever machine connected to your network. And then this machine can simply claim that, okay, look, if you're looking for this IP address, which by the way is the IP address of this computer, then this, you can find it using this hardware address. Oopsie, but that's the hardware address of this machine. And you can also tell, okay, it's also you yourself, you also have this, well, you tell this, the other one, if you want to send something to this machine, or no, you use this hardware address. So in the end, all the traffic on layer 2 is redirected directly to this malicious node. Only because this node sent ARP replies, poisoning the caches, because now you have wrong entries in the cache. And so in the end, you have something that's called a man-in-the-middle attack. You could even, well, block the traffic, but you can also forward it so that no one will even notice that the data now flows through this man-in-the-middle, this malicious node. So this is one way of attacking such a cache. And the problem is, what can you do against it? If you have no authentication, it's difficult, it's impossible. I mean, because you just reply faster. And if you don't know who replies, you have to trust the reply. Okay, so if you have an unchanged ARP, no authentication, this may happen. You can check the ARP on your machine. So that's quite simple. There's a command called ARP, and this displays the entries in the ARP cache, and this is exactly where you see those pairs of an IP address and the layer 2 address. This is called the physical address, but in fact it's the link layer address, so layer 2 MAC address. It's not a layer 1 address. Layer 1 address is your plug, your cable. Okay, there's also the reverse operation. Just to show you this and then give you some hints why this is not really necessary. But so there is a protocol, reverse address resolution protocol, and this can be used if the machines don't know their IP address. If you just boot them, they have just their network interface card, a hardware adapter, and the hardware adapter has we call a burned-in address. So it's pre-configured by the manufacturer, for example. You have a certain hardware address. So you don't know where's the IP address, but we need the IP address to use layer 3 protocols. We will see how this problem is solved with IP version 6. Here, assuming IP version 4, we don't have an IP address. So all we can do is sending packets to everyone telling, okay, I'm the one with this hardware address. Does anyone know my IP address? And then you can have a reverse ARP server. And this server now may have a list sending back the IP address. Yes, we can also send back wrong addresses, etc. So that's a very, very basic, very simple scheme. The point is today, for most of the machines, you don't need this. You can replace this by DHCP. I will come back to this. And DHCP has many more features. But this is a reverse ARP is a very simple way of receiving the IP address. But again, we have to trust the server, etc. One of the problems here again is ARP, reverse ARP, they use this layer 2 broadcasts. Routers do not forward this. So if you have such a simple solution, you always need someone to answer within this local area network. So you have to have your reverse ARP server in the local area network. So what is the solution here? That's exactly DHCP is one of the solutions, Dynamic Host Configuration Protocol. This is the typical protocol used today for many, many, many machines. This is what your DSL router knows, DHCP assigning IP addresses to your machines at home. So reverse ARP requests are not passed on by routers, but we don't want to have servers in all of the networks. DHCP, we can have relays. And the DHCP Discover, I will come back to this, this can be relayed into other networks. So we do not need DHCP servers in all the local area networks. So we may have only one server and you have something that's called a relay. And if someone sends a DHCP Discover, in a second more about this, then via a broadcast, you can relay this over other networks into then the network with the DHCP server. So there's a relay agent. So that's the idea how you solve the problem that you do not want to have a DHCP server on all the local area networks. Maybe in a company you have one DHCP server assigning the addresses, but not in all the local area network. So also the DHCP server can do more than just giving you the IP address. DHCP can configure subnet masks, default router, DNS servers, all the things you know already. Someone has to tell the machines. And in a long time ago, 30 years ago, you had to do this by hand. Subnet mask and routers, you had to enter all these things. DHCP solves all these issues. Okay, so DHCP, how does it work? DHCP, a little bit more modern, 1997. First of all, there's a service discovery. So if you don't know what your MAC address is, now let's assume the computer C doesn't know anything, then you send out a broadcast, DHCP discover. Okay, this is my MAC address. So this is something you know from your hardware. What is my IP address? I need the IP address. Same as with ARP. So, but now we can have several DHCP servers. So for example, for redundancy reasons, you don't have to have several, but for redundancy reasons, maybe it's a good idea. Then those servers can send back a so-called DHCP offer. And this is now unicast and not a broadcast anymore, because they know who asked for the address. And then this offer contains, okay, look, this is an IP address, plus this is the net mask, plus this is a default router, etc. Okay, so that's the phase one. You can have several of these servers. So now phase two, well, okay, I pick a C, I pick one of the addresses and broadcast this and tell now everybody, okay, listen, this is my MAC address and I want to use this IP address because, okay, that's one of the choices I have made by the different DHCP servers. Okay, and if no one complains, you will get an acknowledgement. Yes, you can use this IP address, and the server offering this IP address will then basically mark this address as, okay, that's the computer using this address. You can assign this permanently, so many of the routers allow you to tell them for the DHCP server, okay, click as use this permanently as the IP address, or only lease it for a limited period of time. And after expiration, you have to renew the lease. You can free the address, etc. So that's the idea. And there's also another benefit that with using DHCP, you don't need that many addresses because you only need IP addresses for active devices in your network. And if you're a company with many, many mobile devices, for example, they are not all active. Maybe it's different at your home. You have one fixed IP address for your printer and one for your desktop computer and one for this mobile phone, etc. But for larger organizations, this is quite common that you have many more devices, especially mobile devices, than devices actively using the network. Okay, so how does it work, this interaction? On the left-hand side, we have the DHCP server and we have a client. And there are also well-known ports for DHCP. And so first of all, the client has to say, okay, DHCP discover. So I broadcast basically to everyone, I'm looking for an IP address. Okay, and now one or more servers can answer and say, okay, look, that's me. That's exactly the source address of this DHCP server. It also goes to everyone to broadcast, but to a certain port. That's exactly this port here. And then I propose a certain IP address, internet address. Okay? And then the client has a certain proposal and says, okay, is this a good idea using this 223.1.124 for 1 hour? And then I say, okay, why not? Let's take this one. And now I accept this request and you will get the acknowledgement. So this is the way how it's done, this transaction. And now I've got in the end, I've got the IP address for 1 hour. And then I have to renew it. You can also renew by hand. So there are different commands really for the command line where you can type renew and then you will get a new IP address, for example. So that's the idea. And you have always, as you see, transaction identifier so that the computers know which request response belong together. 654 and 655. Okay, DHCP also has a certain format. That's just for information. If you're interested in details, please look it up in literature. So this is what's all sent, the transaction ID, and then all the IP addresses, the hardware addresses, the host names, etc., and many options. There are too many options to go into all the details. So not only options like subnet masks and host names and name server and maybe printer, and you see there's so many different things that can be specified, many different messages like the requests, like the acknowledgement, release, and all these things. The key idea is that the server stores a pool of addresses and then takes out one address from this pool. And as I said, the pool can be smaller than the number of mobile devices, for example, in a company. And then you have this mapping, and you can even log this so that you know which machine got which MAC address at which time. So that's the idea. Okay, so there are different events like this discover and DHCP request, etc., and what action is taken. But this already have shown you with this message sequence chart. So that's the idea. So simple, but way more powerful than just, well, this simple reverse address resolution protocol. So here you can get a lot more. A bit more about DHCP. DHCP also has quite some problems. Okay, it's unreliable. It's all client-driven, so the clients do this, and well, you don't know if it works, then you have to retry, etc. There's a DHCP for IP version 6, DHCP version 6. But all the DHCPs, they also have some security issues at least. So what about unauthorized clients? What happens if, because it's client-driven, if malicious clients exhaust the address pool? So if you just request all the time, then you don't have any addresses available. Then it takes some time before you free the addresses again, etc. And during this time, no one can connect to the network. There could be also malicious servers that provide incorrect configuration parameters. So what happens if someone just claims to be the DHCP server? You just have to be faster than the official one, and then you could send out strange configurations. So there are some issues. Okay, so what has changed for IP version 6? So DHCP is the dominant protocol for version 4, but IP version 6 can do a bit more. And to learn a bit more about what IP version 6 can do, we have to learn that IP version 6 has a built-in neighbor discovery. So neighbor discovery, what's the basic idea? So neighbor discovery, that's typically that routers tell into the network, hey, that's me, I'm your router, and by the way, this is your network. Telling into the network prefix, among other parameters. This helps, for example, mobile devices. As soon as you enter the network, or any other device, if you enter the network, you connect, you receive automatically these advertisements, and then you can learn, this is the network I'm in. Is this my original network? Or if maybe I'm now at a foreign network, I will come back to this in mobile communications. So, neighbor discovery is a key mechanism in IP version 6. We learned that we can do this router discovery with it, prefix discovery, so prefix, the important network part of my IP address. We learn that with the help of neighbor discovery, we can replace ARP, so for address resolution. We can also redirect traffic. So how does all this work? Well, neighbor discovery uses a protocol, and that replaces our ARP, can do a bit more. So not only address resolution. So neighbor discovery can detect reachability, so neighbor reachability detection, auto configuration. We have a close look into all this. So router discovery, which one is the router, and many other things, duplicate address detection, etc. So we can do a bit more. And with the help of this NDP, we can do something that's called stateless address auto-configuration. And that's a replacement for DHCP. So address resolution protocol, the idea was, okay, I've got an IP address. What is the MAC address? That was ARP. I will just show you some examples for this. And DHCP was, well, I don't have any configuration. Please send me a lot of configuration so I can talk with the environment, among others, the IP address and all these things. So IP version 6 doesn't need a special server for this. So stateless address auto configuration works without any special server and can still configure the IP version 6 address. This is based on NDP. How does it work? Some examples. Okay, so this example, we have here our computers with MAC address, MAC 1, and you see the long IP version 6 address, and the other computer also with IP version 6 and MAC address. So, okay, if I don't know where the neighbors are, I can do something that's called neighbor solicitation. So basically neighbor solicitation, this is now the name for what we called before our ARP request. So I've got an IP address and I want to know the MAC address. And here we have a special format of the IP address I'm asking. So I know this is the IP address I'm looking at, and I will not send this complete IP address, but this is a special format here. That's for my neighbor solicitation, our ARP request. And then I will get my ARP reply, my response here, telling, okay, in the end, this is the MAC address that belongs to this IP address. So that's the idea here, that we have a special address. So we do not have a special protocol like ARP, but we have now, because we have so many bits for addresses, a special address that works as, well, ARP request. And so the neighbor solicitation, so our ARP request, well, it's not called the ARP request, but that was the ARP request for IP version 4. Now the neighbor solicitation uses a special solicited node multicast address, FF02, and so on. So instead of developing a separate protocol, we now use a special address out of those many addresses. And the remaining bits then code the LSB, the least significant bits of the requested IP version 6 address. The other computer in my network. So that's the idea of the neighbor solicitation. That's the equivalent of the ARP request, and the neighbor advertisement, the equivalent of the ARP reply. And that's the idea, that now we have many addresses, we have special addresses that replace protocols, which makes life much easier. You don't have to implement a special protocol, but you use special addresses. So, and this is what we can do with this neighbor discovery protocol. We can do our what was formerly called ARP, our neighbor solicitation and neighbor advertisement, and also router advertisements, router solicitation. Router solicitation, the idea is to trigger a router advertisement, and the router advertisement itself, that's quite important. As I said before, routers periodically typically send out, this is the local area network. So they send out the prefix so that you as a host system know already, that's the network I'm in. So if you connect a machine, the machine immediately can know, this is this network. And if the routers don't do this, then you send out a router solicitation, then the routers will answer with a router advertisement. And then there are some additional things you can do. And all these messages for this neighbor discovery protocol, all these messages are accomplished via ICMP packets. I will come back to ICMP, that's the Internet Control Message Protocol, but now for version 6. So basically a protocol that is in version 4 only used for control messages, error messages, but now also used for many advertisement, solicitation, etc. functions. That's the idea. So both IP version 4 and IP version 6 need these mapping functions of this is my hardware address, what is the IP address, this is the IP address, what is the hardware address. And we had this IP to MAC, that was our ARP. And now here we have our neighbor solicitation, advertisement, and neighbor cache. That's the equivalent for the ARP cache. Okay, so that's the idea. And we also have like this gracious ARP where we can simply just send out ARP requests without needing them, just to check if everything is okay, duplicate address detection. We have now special things for routers, which was handled with ICMP version 4, now also handled with ICMP version 6. So what is the advantage? Why not having a protocol? Well, first thing is, not having a protocol is a good idea, because then nothing can go wrong in the protocol. We already work on the network layer, and we have basically just special addresses here. So, and using the ICMP version 6, and ICMP is a protocol, but we don't need an additional one, ARP. Another big advantage is that it's all pure network layer. So it's a network layer. So protocol, we can use IP. So there is IP, the IP world, and everything already works on this IP world. ARP not. ARP is a protocol that operates with layer 2 broadcasts. So operates everything on layer 2, but if you remember, you want to send a packet. You have the layer 3 address. But you don't know the MAC address. The only solution in IP version 4 was we have to use a broadcast on this layer 2, and then we will find out layer 3 address. Here we operate already with valid IP addresses, IP version 6 addresses, and all the protocols now operate on top of these addresses, so above IP. So it's there is already layer 3. And the good thing here is we can now apply all layer 3 security mechanisms. I will come back to security later in a separate chapter. So with IP version 6, using these mechanisms, we don't have this ARP spoofing anymore. So we can do all this stuff like encryption, authentication, etc. So network layer security, because we work on top of this. So we don't use a layer 2 protocol like ARP. No, we use layer 3 addresses. And then we can also use layer 3 security mechanisms. So this is one of the big advantages. So we get rid of a separate protocol, so no more ARP as a separate protocol. We only use the ICMP, plus this is all working on top of the IP. So we have IP addresses. Okay, so what else? So how do we get now our IP addresses? So for this ARP equivalent, our solicitation, we assume, okay, we know the address, but how do we get the address? So how do we get our IP version 6 address? And also here we see there's a much smarter solution with IP version 6. So what we do is, first of all, we generate a tentative link local IP version 6 address based on our MAC address. So, because we have so many address bits, we have the MAC address, 48 bits, we can use the MAC address MAC address and generate now a link local address that's only valid in the link. Then we check for duplicate addresses. That's the idea, because we picked a kind of arbitrary address, not really arbitrary, but an address that's based on our MAC address, maybe hashed, etc. And it could be the case that this address we now generated based on MAC hashing, etc., already exists. So we ask our neighbors in the local link, the local network, does this address already exist? Okay. And well, if no one answers, so then we assign the address to the interface. And the key idea now is we can immediately communicate using a valid link local IP version 6 address. Remark, this is not a global IP version 6 address. So we cannot use this address now to send packets around the globe, because the global address has to be unique worldwide. So this is a way of, first of all, finding out a link local address so we can operate already in our link using IP and all mechanisms based on IP. Without the IP address, we cannot use any higher layer protocols. If we have an IP address, then we can use all the higher layer protocols, so TCP and this and that. Okay, only in the local link, but that's fine for now. If the address is already in use, then someone will answer, that's a problem, failure. Then manual configuration. Okay, that's the idea. Okay, so that's the basic idea. Again, why do we do this? If we have an IP address, then we can use all the higher layer protocols. But how do we get an IP address? Well, that's one way of at least having a link local IP address, and then we can do many more things. Okay, so how do we generate this tentative link local address based on MAC address? One way of doing so is we use our 48-bit MAC address from network interface card and map it into a 64-bit identifier. It's described here, so you take the leftmost 24 bits from the MAC and they form the leftmost 24 bits of this 64-bit host ID. Take the rightmost and they form the rightmost 24-bit, and then there's something missing in the middle, and this is where we insert a constant FF, FE, in the middle 16 bits. Then we tweak one of the bits, and that's it. So we have to prepend a link local prefix. Again, you see how we play with the addresses. Because we have so many, we can create, in doing so, create a valid IP version 6 128-bit address, and that's it. So we have the tentative IP version 6 link local address by FE80, many zeros, and then this 64-bit identifier we just created up here. Looks a bit complicated, but that's the way how this is done. So based on our MAC address, we can form this IP address, and then we check for duplicates. So hopefully there's no other adapter using this MAC address, but we never know, because this is, well, should be unique, but you know. So that's the idea. And now, having an IP address, we can now work on with this network layer. You could also do whatever creating this identifier, but that's the way, one way of this is how this is specified. So we have to contact our router. Well, so we have our link local address, and now we ask, okay, we have to communicate with the outside world. So please, where's a router? So it could be the case that we receive router advertisement anyhow, but we could also send out a router solicitation to all the routers. There again is a well-known address, FF02, many zeros and a 1. So this is a router solicitation message IP address, and then routers, or at least hopefully one router, then responds with a router advertisement. Okay, so first I get this link local address. With the help of the address, I can now ask the routers. Routers will answer. Still, we don't have a global IP version 6 address. Now, phase 3 follows. The router advertisement contains different flags, like, well, how the addresses are configured, stateful configuration, etc., etc. Prefixes. Prefix is quite important because this tells me which network I'm in. Now, depending on certain flags, for example, if we have a managed address configuration, we stop here and do a stateful configuration, use DHCP version 6. But we don't have to do this. If this flag M is 0, then we go into stateless configuration. This is why this is called a stateless automatic address configuration, SLAAC. So you see, even without DHCP, we can automatically generate a globally unique address. We take the network ID here and say, okay, great, that's the network ID. And now, well, depending on the other flags, we have now already our address, and we can continue depending on this O flag if we need DHCP version 6 for a name server, for some other things, always simply say, okay, that's enough because I have my address. So that's one of the ideas here, that, okay, based on this, that was the beginning, our link local address that is based on the MAC address, we have already a valid address layer 3, we contact the routers, we get the prefix, then we have the network ID, and this altogether then gives us a globally unique IP version 6 address without the help of DHCP. So we don't need, this is why it's called stateless, etc., because DHCP is stateful. DHCP, we don't need it, but we can integrate DHCP. Then DHCP does all this address configuration, or DHCP does only information for name server, etc. Okay, so going back to this. So how do we get our addresses? That was the key point. So how does a computer get the IP address if you just switch it on? So how do we get the MAC address that belongs to an IP address and vice versa? What are the different versions here? IP version 4, IP version 6. Remember the example. Now with IP version 4 or with IP version 6, you are in Berlin and you try to send a packet to a computer in Tokyo. Which MAC destination address to use? Why is DHCP more powerful than reverse ARP? IP version 6 doesn't have any ARP, so the protocol is missing. What replaces it? What can we do there? And if you compare now the stateless address configuration with DHCP version 6, so why do we need DHCP? Can't SLAAC solve all these problems? So when could we use this maybe simpler version, and when could we use this more complex version, DHCP?